Okay, so it's been a long time. I thought let's study today. Let's have our broadcast today. So let's get back to where we were at that time when we were studying. So we were doing standard streams. The standard IO library defines three special identifiers: C in, C out, and C error. Okay, everybody knows about C in and C out, but what is C error? CERR that acts as string variables and are all available in all programs. These variables are referred to as standard streams. The constant Cin designates the standard input stream, which is the source for user input. The constant Cout indicates the standard output stream and represents the device on which output data is written to the user. The constant C error represents the standard error stream and is used to report any error messages the user should see. Typically, the standard streams all refer to the computer console. When you read the data from C in, the input comes from the keyboard. When you write the data to C out or C error, the output appears on the screen. You do not open or close these streams, they are handled automatically. Formatted stream output. Stream output is usually accomplished by using the insertion operator. The operand on the left is the output stream. The operand on the right is the data being inserted into the stream. Thus far, you have only written to C out, but any open output stream can be used as a designation. The insertion operator will accept any primitive type on the right. Arrays are treated as pointers in this context and only the base address is printed. Strings print the entire sequence of characters. By default, complex types such as structs cannot be printed with a single insertion operation. You must output each of the struct members one by one. Several insertions can be chained together by multiple uses of the insertion operator. The manipulator endl is used to output a new line. Values are formatted according to the stream's default rules unless you specify otherwise. For explicit control, you insert IO manipulators to set the field width, alignment, precision, and other features on a per stream basis. A few common output manipulators options are described in the section on simple output and input in Chapter 1. Although the mechanisms for formatted I/O in any programming language can be quite useful, they also tend to be detail ridden. I recommend having a reference on hand for looking up details on as needed basis rather than memorizing the entirety of the options. Formatted stream input, the extraction operator. Oh, that was insertion operator? Yeah, this is extraction operator. We are extracting something from somewhere. Provides an input counterpart to the insertion operator and allows program to read in values of the various basic types. Here is the simple usage of reading an integer from an input stream. The operand on the left is the input stream and the operand on the right is the variable that will store the value read from the stream. The previous value of the variable is overwritten by the next integer read from the stream. The default setting for an input stream is to skip characters that appear as blank space, such as the space, tab, new line characters. When reading the next value, the insertion operator will skip over any leading blank space and start reading from the first non-blank character. When extracting a string from an input stream, a sequence of non-blank characters is read, stopping at the first blank. To illustrate how blank space is handled, consider the text file with the following contents: 3 space 45 space some text. If you do int num1 num2 strings str and then char ch and you do like that, after executing this code, num1 would hold 3, num2 will hold 45. str would hold some and ch will be t, not text. Okay. The extraction operator will fail if there is no input remaining or if the next input is not compatible with the type you are attempting to extract. Hmm. The stream method fail can be used to test whether an extraction operation was successful. If you were attempting to read and sum integers from a file until you reach the end, you could use a loop such as this one, total equals to true, total equals to 0, while true in file, and extract it into the num. If in file not fail, break total plus equals num. Okay, yeah, we can do that. For a program to be robust, it typically must take care to handle malformed input. This is especially important when reading from CN, where the human user is prone to typing errors at the console. To avoid cluttering the code with error handling, this text does not use the extraction operator on CN and relies instead on the facilities provided by the simpio.h interface described on chapter 1 that have error handling built in. Single character IO. Most IO is handled with the insertion and extraction operators, but there are times when it is more convenient to process files as a sequence of characters or lines. The method get is used to read a single character from an input stream. Although the idea of get seems simple enough, there is a confusing aspect in its design. If you look at the formal definition of get, its prototype looks like this: int get parenthesis. At first glance, the result type seems odd. The prototype indicates that get returns an integer, even though conceptually the function returns a character. The reason for this design is that returning a character would make it impossible for a program to detect the end of the file mark. There are only 256 possible character codes, and a data file might contain any of those values. There is no value, or at least no value of type char, that you could use as a sentinel to indicate the end of the file condition. By extending the definition so that get returns an integer, the implementation can return a value outside the range of legal character codes to indicate the end of the file condition. That value is given the symbolic name of EOF. Okay, that's pretty cool. Common pitfalls. Remember that get returns an int, not a char. If you use type a variable of type char to store the result of get, your program will be unable to detect the end of the file condition. For output streams, the method put takes just one argument, a single character, and writes that character to the stream. As an example of the use of get input, you can copy one file to another by calling the following function: void copy file is istream in file ostream out file int ch, while ch equals in file dot get not equals to end of the file outfile dot put ch. The while loop in the copy file is highly idiomatic and deserves same consideration. The test expression for the while loop uses embedded assignments to combine the operations of reading in a character and testing for end of the end of the file condition. When the program evaluates the while condition, it begins the sub expression ch equals infile.get, which reads a correct character and assign it to ch. Before executing the loop body, the program then goes on to make sure the result of the assignment is not EOF. The parentheses around the assignment are required Without them, the expression would incorrectly assign to CH, the result of comparing the character against EOF. Note that both stream parameters are passed by reference to the function copy file. Reading from and writing to a stream changes its internal state, and it is essential to pass streams by reference so that the stream state is consistently maintained throughout the context of the entire program. Rereading characters from an input file. When you are reading data from an input file, you will often find yourself in the position of not knowing that you should stop reading characters until you have read more than you need. For example, suppose that you are asked to write a program that copies a program from one file to another, removing all the comments as it does so. As you know, a comment in C++ begins with the character and ends with the character. A program to remove them must copy characters until it detects the initial this and then read the characters without copying them until it detects this. The only aspect of this problem that poses any difficulty is the fact that the comment markers are two characters long. If you're copying the file a character at a time, what do you do when you encounter a slash? It might be the beginning of a comment, in which case you should not copy it to the output file. On the other hand, it might be the division operator. The only way to determine which of these cases applies is to look at the next character. If it's an asterisk, you need to ignore both characters and make sure of the fact that a comment is in progress. If it is not, however, what you would most like to do is forget that you ever read that character and then treat it normally on the next cycle of the loop. The stream interface provides a function that allows you to just do that. The method is called unget or unget has the following form. The effect of this call is to push the last character reads back into the input stream so that it is returned onto the call to get. The C++ libraries only guarantee the ability to push back one character into the input file, so you should not rely on being able to read several characters ahead and then push them all back. Fortunately, being able to push back one character is sufficient in the vast majority of cases. An implementation of a function copy removing comments that uses unget is shown in figure 3.7. Line oriented IO. Because files are usually subdivided into individual lines, it is often useful to read an entire line of data at a time. The stream function that performs this operation is called getLine, not to be confused with the similarly named getLine function from the SIMPIO interface. Unlike the other stream operations we have discussed, getLine is not a method and is not invoked using dot notation. GetLine takes two arguments, the input stream to read from and a string that are both reference parameters. So there is a piece of code which I'm not really able to understand. So let's understand it by putting out ChatGPT.
वो जो स्कूल के डिबेट कंपटीशन जैसा होता है। पहले एक साइड जो बोलता है, फिर दूसरा साइड उसका उल्टा बोलता है। अभय और कौस्तव भी ऐसे लड़ते थे। अभय कौस्तव से बहुत गुस्सा थे, लेकिन हर मीटिंग में आती थी। और जब दूसरा बार कौस्तव कुछ बुरा बोलता था, तो आगे बढ़कर लेती थी।
Okay, unget is used to put the character back into the string. So basically, we are saying get the character. If it is not the end of the file, then check if we got the comment flag, because the comment flag is that forward slash. If after the comment flag we got the character to be the star, then we will get the next character of that. After getting the next character, that is another forward slash, that means the comment is ended. So we make it false. Else we didn't find the ending, that means the comment is going on. And if the comment is going on, do we need that? We don't. So we will do in file dot unget. Whatever we got, we will unget that. Right. So then else if the character is forward slash, we will get the next character. If it is a star, that means it is a comment. So we make the comment flag as true. Else we will unget. If the comment flag is false, then we will do out file dot put char. Yeah, true. Because we need to put from one file to another. And if it is a normal character, we will put it normally. So that's fine. Okay. The effect of this function is to copy the next line of the file into the string parameter. Get line removes the new line character used to signal the end of the line, so that the string contains simply the characters on the line. The string will be empty string if the next character coming up in the string is a new line. The getLine function will fail if there are no more lines to be read from the file. As always, you can test whether the stream is in a failure state using fail method. Some of the most common operations exported by the IOStream and FStream interfaces are summarized below. File.open file name. This method attempts to open the named file and attach it to the receiver stream file. Note that the file name parameter is a C style string, not a C++ string object. You can convert a C++ string to a C style equivalent with the string method cstr or with the string method cstr. Oh, okay. Oh, here's the thing. Yeah, the file name needs to be a C style string, not a C++ style string. Okay, so it cannot be initialized as string and then like that. You can check whether open fails by calling the fail method. File.close. This method closes the file attached to the stream file. File.fail. This method returns a boolean indicating the error state of the stream file. A true result means that a previous operation on this stream failed for some reason. Once an error occurs, the error state must be cleared before any further operations will succeed. File.clear. This method clears the error state of the stream file. After an error, you must clear the stream before executing subsequent operations. That means once you do file.clear, you will always, once you do file.fail, you will always do the next step as the file.clear. In file.get, this method reads and returns the next character from the input stream in file. If there are no more characters, get returns the constant EOF, end of the file. Note that the return value is of type int, not char. In file.unget, this method pushes the last character read back onto the input stream in file. GetLine in file str. This function reads the next line from the input stream in file into the reference parameter str, discarding the new line. Note, this is not a method but an ordinary free function. This is a different function than getLine from simpio.h. In file var, the stream extraction operation reads a value into var from the input stream in file. By default, leading whitespace is skipped. If there is no input remaining or the next input is not compatible with the type of the var, the stream is set into an error state. Outfile.putch if the method writes the character ch to the output stream outfile. Outfile expression. This stream insertion operations writes the value of expression to the output file, output stream outfile. The expression can evaluate to any type that has a defined stream insertion behavior. Generally, this means all primitive types and string. Other ANSI libraries. In addition to the string and F-stream interfaces described earlier in this chapter, there are a few other interfaces in the standard library that are important for you to know. The most important of these are the C-type interface, which exports a set of functions for working with characters, and the CMath interface, which exports several common mathematical functions The most important functions exported by these interfaces are shown in tables. Common functions exported by the CC type interface is upper. These functions returns true if CH is an upper letter or a lowercase letter or any type of letter respectively. So is upper, is lower, and is alpha. Is digit. This function returns true if CH is one of the digit characters. Is LNum is going to return true if the CH is alphanumeric, which means that it is either a letter or a digit. Is punct means it will be true if it is a punctuation symbol. Is space will be true if it is a white space character or it's a backslash t, backslash n, backslash f, backslash v, all of which appear as blank space on the screen. Is print ch. This function returns true if ch is any printable character, including the white spaces. 2 upper, 2 lower will convert to the desired case so that okay. If not, ch is returned unchanged. Common functions exported by the math interface. Oh. Fabs. This function returns the absolute value of a real number x. The function abs, which takes the absolute value of an integer, is exported by cstdlib. Floor. This function returns the floating point representation of the largest integer less than or equals to x. And ceil will return the smallest integer greater than or equals to x. F mod x comma y. This function returns the floating point remainder of x divided by y. Floating point remainder of x divided by y. So it's basically the modulo operator. SQRT. This function returns the square root of x. Pow x comma y. This function returns x raised to the power y. EXPX. This function returns e raised to the power x. Log x. This function returns the natural logarithm of x. Sine theta cos theta. This function returns the sine and the cosine of the angle theta, which is expressed in radians. You can convert from degrees to radians by multiplying by pi divided by 180. A tan x. This function returns the trigonometric arc tangent of the value x. The result is an angle expressed in radians between minus pi by 2 to plus pi by 2. A tan 2y comma x. This function returns the angle formed between x-axis and the line extending from the origin through the point x comma y. As with the other trigonometric function, the angle is expressed in radians. In some cases, the functions in these interfaces are easy to implement on your own. Even so, it is good programming practice to use the library functions instead of writing. These are 3 principal reasons for doing so. Because the library functions are standard, programs you write will be easier for other programmers to read. Assuming that the programmers are at all experienced in C++, they will recognize these functions and know exactly what they mean. It is easier to rely on the library functions for correctness than on your own program. Because the C++ libraries are used by millions of client programmers, there is considerable pressure on the implementers to get the functions right. If you rewrite library functions yourself, the chance of introducing a bug is much larger. The library implementations of functions are more often efficient than those you can write yourself because these libraries are standard and their performance affects many clients. The implementers have a large incentive to optimize the performance of the libraries as much as possible. In this chapter, you have learned about interfaces, which are the points of connection between client of a library abstraction and the corresponding implementation. Interfaces are one of the central themes of modern programming and will be used extensively throughout the rest of this text. You have also learned how to use several specific interfaces like random.h, string, fstream, cctype, and cmath. Important points in this chapter include an interface provides a channel of communication between a client of a library and its implementation, but also acts as a barrier to keep unnecessary information from crossing the boundaries between the two sides. Interfaces in C++ are represented using header files. The definitions exported by an interface are called interface entries. The most common interface entries are function prototypes, constant definitions, and the type definitions. The interface should contain extensive comments for each entry so that the client can understand how to use that entry, but should not expose details that are relevant only to the implementation. A well designed interface must be unified, simple, sufficient, general, stable. Because these criteria sometimes conflict with each other, you must learn to strike an appropriate balance in your interface design. You can use the random.h interface to generate pseudo random numbers that appear to be random even though they are generated deterministically. The random.h interface exports four entries: random integer, random real, random chance, randomize. The interface string provides a string class and abstraction used for manipulating sequence of characters. The strutils.h interface adds some convenience operations on strings. The fstream interface exports operations that allows you to read and write data files. The process of using a data file consists of four steps: declaring a stream variable, opening the file, transferring data, and closing the file. Review questions, interface, package, abstraction, implementation, and client. In your own words, describe the difference in perspective between a programmer who writes implementation of a library and one who writes programs that are clients of that library. Uh, the interfaces. So let's look at the syllabus. So for the first week, there will be a course overview, C++ fundamentals, and that means the chapter 1, 2.1 till 2.4. In the first week itself, they are going till 5.1. What? Oh no, I'm so behind. How will I wait? I'm done with the chapter 3, by the way, just now. If I move to the chapter 4, I should be able to do everything till 5.1. Will I even teach him that? Okay, not hard for me, but how are we going to complete it? That's the thing. There's like 15 chapters. Seriously? We do have 15 chapters, is it? have 16, not even 15. Nice. And how are we going to do it till August 11 to 15? This is like too fast. What is that? Okay, let's do chapter number 4. We'll do it. It's fine. We also have some videos, lectures. We can actually try to look for that. That what they are teaching. So I need to design it like that so that we can complete it. We'll do that. Chapter 4, using abstract data types. So nothing remained in whose reality she would believe save those abstract ideas. As you know from your programming experience, data structures can be assembled to form hierarchies. The atomic data types such as int, char, double, and enumerated types occupy the lowest level in the hierarchy. To represent more complex information, you combine the atomic types to form larger structures. These larger structures can then be assembled into even larger ones in an open ended process. Collectively, these assemblages of information into more complex ideas or more complex types are called data structures. As you learn more about programming, however, you will discover that particular data structures are so useful that they are worth studying in their own right. Moreover, it is usually far more important to know how those structures behave than it is to understand their underlying representation. For example, even though a string might be represented inside the machine as an array of characters, it also has an abstract behavior that transcends its representation. A type defined in terms of its behavior rather than its representation is called abstract data type. So basically, we are talking about behaviors, not the representation, which is often abbreviated as ADT. Abstract data types are central to the object oriented style of programming, which encourages thinking about data structures in a holistic way. In this chapter, we will have a chance to learn about 7 classes: vector, grid, stack, queue, map, lexicon, and scanner, each of which represents an important abstract data type. For the moment, we will not need to understand how to implement those classes. In subsequent chapters, you will have the chance to explore how each of uh, these classes can be implemented and to learn about the algorithms and data structures necessary to make those implementations efficient. Being able to separate the behavior of a class from its underlying implementation is a fundamental precept of object oriented programming. As a design strategy, it offers the following advantages: simplicity. Hiding the internal representation from the client means that there are fewer details for the client to understand. Flexibility. Because the class is defined in terms of its public behavior, the program who implements one is free to change its underlying private representation. As with any abstraction, it is appropriate to change the implementation as long as the interface remains the same. Security. The interface boundaries acts as a wall that protects the implementation and client from each other. If a client program has access to the representation, it can change the values in the underlying data structure in unexpected ways. Making the data private in a class prevents the client from making such changes. The ADT classes used in this book are inspired by and draw much of their structure from a more advanced set of classes available for C++ called Standard Template Library, STL for short. Although the STL is extremely powerful and provides some capabilities beyond the somewhat simplified class library covered in this book, it is also more difficult to understand from both the client and implementation perspectives. One of the primary advantages of using the simplified class library is that you can easily understand the entire implementation by the time you finish this book. Understanding the implementation gives you greater insight into how classes work in general and what libraries like the standard template library are doing for you behind the scenes. Experience has shown, however, that you will be able to understand the implementation of a class more easily if you have first had a chance to use what with that class as a client. The vector class, one of the most valuable classes in the standard template library, and the simplified version of it used in this book is the vector class, which represents a generalization of the array concept represented in section 2.4. To use the vector class, you must include its interface just as you would for any other libraries. The interfaces for each of the ADT classes introduced in this chapter is simplify the name of the class spelled with the lower initial letter and followed with the extension .h at the end. Every programmer that wants to use vector class must therefore include the line #include quotations vector.h. Arrays are a fundamental type in almost all programming languages and have been part of programming language design since the beginning of the fields. Arrays, however, have a number of weaknesses that can make using them difficult, such as the following. Arrays are allocated with a particular size that doesn't change after the size is allocated, after the array is allocated. Even though arrays have a fixed size, C++ does not in fact make that size available to the programmer. In most applications, you need to keep track of the effective size of the array. It is impossible to insert new elements into an array or to delete elements without writing a fair amount of code to shift the existing elements to new index positions. Many languages, including both C and C++, make no effort to ensure that the elements you select are actually present in the array. For example, if you create an array with 25 elements and then try to select the value at index position 50, C++ will not ordinarily detect this as an error. Instead, the program will blithely go on and look at the memory address at which element 50 would appear if the array were long enough. It would be far better if arrays in C++, as they do in Java, implemented bounds checking, which means that every array access checks to see whether the index is valid. The vector class solves each of these problems by re-implementing the array concept in the form of an abstract data type. You can use the vector class in place of arrays in any application, usually with surprisingly few changes in the source code and only a minor reduction in efficiency. In fact, once you have the vector class, it's unlikely that you will have much occasion to use arrays at all, unless you actually have to implement classes like vector, which not surprisingly uses arrays in its underlying structure. As a client of the vector class, however, you are not interested in that underlying structure and you can leave the array mechanics to the programmers who implement the abstract type. As a client of the vector class, you are concerned with a different set of issues and need to answer the following questions. How is it possible to specify the type of the object contained in a vector? How does one create an object that is an instance of the vector class? What methods are available in the vector class to implement its abstract behavior? The next three sections explore the answers to each of these questions in turn. Specifying the base type of the vector. Most of the classes covered in this chapter contain other objects as part of a unified collection. Such classes are called either container classes or collection classes. In C++, container classes must specify the type of the object they contain by including the type name in angle brackets following the class name. Wait 1 second, let me check something. I think that's okay. In C++, container classes must specify the type of the object they contain by including the type name in angle brackets following the class name. For example, the class vector angular brackets int represents a vector whose elements are integers. Vector char represents single character elements, while vector string specifies one in which elements are strings. The type enclosed within the angle bracket is called the base type for the collection and is analogous to the element type of a conventional array. Classes that include a base type specification are called parameterized classes in the object oriented community. In C++, parameterized classes are more often called templates, which reflects the fact that C++ compilers treat vector int, vector char, vector string as independent classes that share a common structure. The name vector acts as a template for stamping out a whole family of classes in which the only difference is what type of value can appear as an element of the vector. For now, all you need to understand is how to use templates. The process of implementing basic templates is described in chapter 9. Declaring a new vector object. One of the philosophical principles behind abstraction data types is that clients should be able to think of them as if they were built in primitive types. Thus, just as you would declare an integer variable by writing a declaration such as int n, it ought to be possible to declare a new vector by writing vector int vec. In C++, that is precisely what you do. That declaration introduces a new variable named vec, which is a template marker in angular brackets indicates a vector of integers. As it happens, however, there is more going on in that declaration that meets the eye. Unlike declarations of the primitive type, declarations of a new class instance automatically initializes the object by invoking a special method called a constructor. The constructor for the vector class initializes the underlying data structures so that they represent a vector with no elements, which is called an empty vector, to which you can later add any elements you need. As a client, however, you have no idea that those underlying data structures, what those underlying data structures are. From your point of view, the constructor simply creates a vector object and leave it ready for you to use. Operations on the vector class. Every abstract data type includes a suite of methods that define its behavior. The methods exported by the vector class appears in table 4.1. As you can see, the vector class includes methods that correspond directly to standard array operations, selecting an individual element and determining the length, along with new methods that extend the traditional array behavior, adding, inserting, and removing elements. Given that every vector you create starts out with no elements, one of the first things you need to learn is how to add elements to a vector object. The usual approach is to invoke the add method, which adds a new element at the end of the vector. For example, if vec is an empty array of integers as declared in the preceding section, executing the code A vec.add will create a 3 element vector. Okay, yeah, that's fine. So we have size as the method returns the number of elements in the vector. Is empty returns true if the vector is empty. Get at index returns the element of a vector that appears at the specified index position. As a convenience, the vector class also makes it possible to select an element using array notation. Using vec square brackets I selects the element of vector at a position I. Set at sets the element at the specified index to the new value. Attempting to reset an element outside the bounds of the vector generates an error. Add value adds a new element at the end of the vector. Insert at index and then the value. Insert the new value before the specified index position. Remove at deletes the element deletes the element at the specified index position. Clear removes all elements from the vector. Iterator returns an iterator that cycles through the elements of the vector in turn. Okay. So first of all, add will add the element at the end of the vector. Insert at, and then you can insert at a specific position. Remove at, you can remove the element at a specific position. Get at, get the element at a specific position. And it will also give you an error if that position is not there. Set at will set an element at a specific position. Now that you have a way of getting elements into a vector, it would be useful to know that how to examine them once they are there. The counterpart to array selection in the vector class is the getA method, which takes the index number and returns the value in that index position. For example, given the most recent of vec, calling vec.getAt2 would return the value 30. If you were to call vec.getAt5, the bound checking code in the vector implementation would signal an error because no such element exists. Hmm. Yeah. Okay. Even though the getAt and setAt methods are relatively simple to use, hardly anyone in fact calls these methods directly. One of the characteristics of C++ that sets it apart from most other languages is that classes can override the definition of the standard operators. In particular, C++ allows classes to override the selection operator used to select elements in an array. This feature makes it possible for the vector class to support exactly the same selection syntax as arrays. To select the element as at a position I, all you need to write is vec I. To change an element, all you need to write is this. The resulting syntax is marginally shorter but considerably more evocative of the array operations that the vector class tries to emulate. Iterating through the elements of a vector. As with the conventional arrays, one of the most common programming patterns used with vectors is iteration, in which you cycle through each of the elements in turn. The basic idiom for doing so is this. Inside the loop body, you can refer to the current element as vec I. As an element, as an example, the following code writes out the contents of the vector vec as a comma-separated list enclosed in square brackets. True. If you were to execute this code, you would see this in the screen, passing in a vector as a parameter. The code at the end of the preceding section is so useful, particularly when you're debugging and need to see what values the vector contains, that it would be worth defining a vector that does it. At one level, encapsulating those lines as a single function is easy. All you have to do is add the appropriate function header like this. As described in chapter 1, the ampersand before the parameter name indicates that the argument to print vector is passed by reference, which means that the vector in the caller is shared with the vector in the function. Passing by reference is more efficient than C++ default model of passing by value, which specifies that the entire contents of the argument vector must be copied before passing it along the function. More importantly, passing by reference make it possible for you to write function that changes the content of a vector. As an example, the following function adds the element of the integer array to a vector. Yeah. If you had left out the ampersand in this header line, the function would have no effect at all. The code would happily add the first 10 elements from the array to the vector, but that vector would be a copy of the one that caller supplied. As soon as the add array to vector returned, that copy would go away, leaving the original value unchanged. This kind of error is easy to make, and you should learn to look for it when your programs go away. The refFile.cpp program shows a complete C++ program that uses vector to reverse the lines in a file. Common pitfalls. When you're using the classes in the template library, you should always pass them by reference. The C++ compiler won't notice if you don't, but the results are unlikely to what you intend. So, if stream in file ask user for input file, vector string lines, what am I doing? Okay, the grid class. Just as the vector class simulates and improves upon a single dimensional array, the grid class is designed to provide a better implementation of a two-dimensional array in C++. As with vector, the grid class contains individual elements, which means that you need to use parameterized type templates to specify the base type. Thus, if you want to create a two-dimensional grid that contains characters, the appropriate class name would grid char. The discipline for creating a new grid object is slightly different from that of a vector, mostly because clients tend to use the grid class in a different way. Particularly when you're reading in elements of a vector from a file, as was true in refFile.cpp, it seems natural to start with an empty vector and then add new elements as you go along. For the most part, that's not the way people use two-dimensional arrays. In most cases, you know the size of the two-dimensional array that you want to create. It therefore makes sense to specify the dimensions of a grid object when you create it. In the grid class, the most commonly used constructor takes two arguments which specify the number of rows in the columns. When you declare a grid variable, you include these arguments in parentheses after the variable, as in a method call. For example, if you want to declare a grid in these with 3 rows and two columns in which each value is a double, you could do so by issuing the following declaration: grid of double matrix 3, 2. That even though the elements of the matrix are created by the constructor, they may not be initialized in any helpful way. If the elements of the grid are objects, they will be initialized by calling the default constructor for that class, which is simply the constructor which takes no arguments. If the elements, however, are of a primitive type like double, C++ does not initialize them, and their values depend on whatever happened be in the memory locations to which those variables were assigned. It is therefore a good memory programming practice to initialize the elements of a grid explicitly before you use them. So instead of storing a junk value by default into a grid, you can actually define all the elements the grid will contain normally. Because so many games, including chess, checkers, and Go, are played on two-dimensional boards, the grid class is often useful in application that plays those games. One particularly simple grid based game is tic tac toe, which is played on a board with 3 rows and 3 columns as follows. Player takes turns replacing the X and O in the empty squares, trying to line up 3 identical symbols horizontally, vertically, or diagonally. Num rows and num columns, these methods return the number of rows and number of columns in a grid, respectively. Get a row column will return the element at that row and a column index. As a convenience, the grid class also makes it possible to select an element using array notation so that grid row call selects the element at the specified location. Set a row call value. Set the element at the specified index to the new value. Attempting to reset an element outside the bounds of the vector generates an error. Resize rows, columns changes the dimensions of the grid as specified by the rows and columns parameters. Any previous contents of the grid are discarded. Iterator returns an iterator that makes it easy to cycle through the elements of the grid. If you want to represent a tic-tac-toe board using the classes provided in this chapter, the obvious approach is to use grid with 3 rows and 3 columns. Given that each of the elements contain a character, an X or O, or a space, the declaration of the board will presumably look like this: grid char board 3, 3. You'll have a chance to see and program that plays tic-tac-toe in chapter 7, but for now, it is sufficient to look at how you might manipulate a tic-tac-toe board declared in this way. Figure 4.2, for example, contains the code for checking to see whether a player has won the game by looking to see whether the same character appears in every cell of a row, column, or a diagonal. Okay. The stack class, one of the simplest class of in the ADT library, is the stack class, which is used to model a data structure called a stack, which turns out to be particularly useful in a variety of programming applications. A stack provides storage for a collection of data values, subject to the restriction that values must be removed from a stack in the opposite order from which they were added, so that the last item added to the stack is always the first time item that gets removed. Because of their importance in computer science, stacks have acquired a terminology of their own. The values stored in a stack are called its elements. Adding a new element to the stack is called pushing that element. Removing the most recent item from a stack is called popping the stack. Moreover, the order in which stacks are processed is sometimes called LIFO, which stands for last in, first out. The conventional and possibly apocryphal explanation for the words stack, push, and pop is that they come from the following metaphor. In many cafeterias, plates for the food are placed in spring loaded columns that makes it easy for the people in the cafeteria line to take the top plate, as illustrated in the following diagram. When the dishwasher adds a new plate, it goes to the top of the stack, pushing the others down slightly as the spring is compressed, as shown. Customers can only take plates from the top of the stack. When they do, the remaining plates pop back up. The last plate added to the stack is the first one the customer takes. The primary reason that stacks are important in programming is that nested function calls behave in stack oriented fashion. For example, if the main program calls a function named f, a stack frame for f gets pushed on the top of the stack frame for main. If f calls g, a new stack frame for g is pushed on the top of the frame for f. When g returns, if its frame is popped off the stack, restoring f to the top of the stack as shown in the original diagram. The structure of the stack class, like vector, grid, stack is a collection class that requires you to specify the base type. For example, stack of int represent a stack whose elements are integers, and same for strings. Similarly, if you had previously defined the classes plate and frame to contain all the information required to represent a dinner plate, and the stack frame for a function, You could represent the stacks described in the preceding two sections with the parameterized class stack plate and the stack frame. The default constructor for a stack class creates an empty stack. The complete list of methods exported in the stack class appears in table 4.3. Stacks and pocket calculators. One interesting applications of stacks is in electronic calculators, where they are used to store intermediate results of the calculation. Although stacks plays a central role in operation of most calculators, that role is easiest to see in scientific calculators that requires user to enter expressions in a form called reverse polish notation or RPN. In reverse polish notation, operators are entered after the operands to which they apply. For example, to compute the result of the expression on an RPN calculator, you would enter the operations in the following order. 50.0, we enter 1.5 and then the multiplication symbol. Then 3.8 and then we enter, and then we do 2.0 and then division symbol and the plus symbol. When the enter button is pressed, the calculator takes the previous value and pushes it onto the stack. When an operator button is pressed, the calculator first checks whether the user has entered a value and if so, automatically pushes it on the stack. It then computes the result of applying the operator by popping the top two values from the stack, applying the arithmetic operation indicated by the button to these values, pushing the result back on the stack. Except when the user is actually typing in a number, the calculator display shows value at the top of the stack. Thus, at each point in the operation, the calculator displays and stack contains the value shown. Methods exported by the stack class. Size returns the number of elements currently on the stack. Is empty returns true if the stack is empty. Push pushes the value onto the stack so that it becomes the topmost element. Pop removes the topmost value from the stack and returns it to the caller. Calling pop on an empty stack generates an error. Peek returns the topmost value on the stack without removing it. As with pop, calling peek on an empty stack generates an error. It removes all the elements from the stack. Clear. To implement the RPN calculator described in the preceding section in C++ requires making some changes in the user interface design. In a real calculator, the digits and operations appear on a keypad. In this implementation, it is easier to imagine that the user enters lines on the console where those lines takes one of the following forms: a floating point number, an arithmetic operator chosen from plus, minus, multiply, divide, and a letter Q which causes the program to quit, H which prints the help message, and the C which clears any value left on the stack. Okay, so because the user enters each number on a separate line terminated with the return key, there is no need for any counterpart to the calculator's enter button, which really serves only to indicate that the number is complete. The calculator program can simply push the numbers onto the stack as the user enters them. When the calculator reads an operator, it pops the top two elements from the stack, applies the operator, displays the result, and then pushes the result back onto the stack. The complete implementation of the calculator application appears here. So apply operator, help command, and clear stack. So we have the int main with the operand stack Okay, so we do the while true, we keep on adding things. We take the input, So if it's a digit, we will call we will do operand stack dot push string to real line. Else we will apply the operator by passing the character and the operand stack. So we have the apply operator function in which we get the RHS and the LHS. We basically pop out two things, and then we already have the operator. If the operator is that, then it's pretty easy. Help command will only show some things like that. Um, Clear stack will just check if the while the stack is not empty, you will keep on popping out from the stack. Okay, now we are at the queue. As you learned in a section 4.3, the defining feature of a stack is that the last item pushed is always the first item popped. As noted in the introduction of that section, this behavior is often referred to in computer science as LIFO, which is an acronym for the phrase last in, first out. The LIFO discipline is useful in programming contexts because it reflects the operation of function calls. The most recently called function is the first to return. But in real world situations, however, its usefulness is more limited. In human society, our collective notation of fairness assigns some priority to being first, as expressed in the maxim first come, first served. In programming, the usual phrasing of this ordering strategy, first in, first out, which is traditionally abbreviated as FIFO. A data structure that stores items using a FIFO discipline is called a queue. The fundamental operations on a queue, which are analogous onto the push and pop operations, are called NQ and DQ. The NQ operation adds a new element to the end of the queue, which is traditionally called its tail. The DQ operation removes the element at the beginning of the queue, which is called its head. The conceptual difference between these structures can be illustrated more easily with a diagram. In a stack, the client must add and remove elements from the same end of the internal data structure. So push and pop is the same side, and that's the top of the stack. In a queue, the client adds the element at one end and removes from the other end. So NQ at the tail of the queue and the DQ from the head of the queue. As you might expect from the fact that the conceptual are so similar, the structure of the queue class looks very much like its stack counterpart. The list of the methods in the queue class shown bears out that supposition. The only differences are in the terminology, which reflects the differences in the order of the elements. The queue data structure has many applications in programming. Not surprisingly, queues turn up in many situations in which it is very important to maintain a first in, first out discipline in order to ensure that service requests are treated fairly. For example, if you're working in an environment in which a single printer is shared amongst several people, several computers, the printing software is usually designed so that all the print requests are entered in a queue. Thus, if several users decide to enter print request, the queue structure ensures that each user's request is processed in the order received. Let's look at all the methods. Size will tell you the number of elements. IsEmpty will tell you if it is empty. NQ will add the value at the tail of the queue. DQ will remove from the head of the queue and returns it to the caller. Calling DQ on an empty queue generates an error. Peak will give you the value without removing it. Calling peak on an empty queue generates an error. Clear will remove all the elements. Queues are also common in programs that simulate the behavior of waiting lines. For example, if you wanted to decide how many cashiers you need in a supermarket, it might be worth writing a program that could simulate the behavior of customers in the store. Such a program would almost certainly involve queues because a checkout line operates in a first in, first out way. Customers who have completed their purchases arrive in the checkout line and wait for their turn to pay. Each customer eventually reaches the front of the line, at which point the cashier total ups the purchases and collect the money. Because simulations of this sort represents an important class of application programs, it is worth spending a little time understanding how such simulations work. Simulations and models. Beyond the world of programming, there are endless varieties of real world events and processes that, although they are undeniably important, are nonetheless too complicated to understand completely. For example, it would be very useful to know how various pollutants affect the ozone layer and how the resulting changes in the ozone layer affect the global climate. Similarly, if economists and the political leaders had a more complete understanding of exactly how the national economy works, it would be possible to evaluate whether a cut in the capital gains tax would spur investment or whether it would exacerbate the existing disparities of the wealth and income. When faced with such a large scale problems, it is usually necessary to come up with an idealized model which is simplified representation of some real world processes. Most problems are far too complex to allow for a complete understanding. There are just too many details. The reason to build a model is that despite the complexity of a particular problem, it is often possible to make certain assumptions that allow you to simplify a complicated process without affecting its fundamental character. If you can come up with a reasonable model for a process, you can often translate the dynamic of the model into a program that captures the behavior of that model. Such a program is called a simulation. It is important to remember that creating a simulation is usually a two-step process. The first step consists of designing a conceptual model for the real world behavior you are trying to simulate. The second consists of writing a program that implements the conceptual model. Because errors can occur in both steps of the process, maintaining a certain skepticism about simulators and their applicability to the real world is probably wise. In a society conditioned to believe the answers delivered by computers, it is critical to recognize that the simulations can never be better than the models on which they are based. The waiting line model. Suppose that you want to design a simulation that models the behavior of a supermarket waiting line. By simulating the waiting line, you can determine some useful properties of waiting lines that might help a company make such decisions as how many cashiers are needed, how much space needs to be reserved for the line itself, and so forth. The first step in the process of line writing a checkout line simulation is to develop a model for the waiting line, detailing the simplifying assumptions. For example, to make the initial implementation of the simulation as simple as possible, you might begin by assuming that there is one cashier who serves customers from a single queue. You might then assume that customers arrive with a random possibility and enter the queue at the end of the line. Whenever the cashier is free, someone is waiting in the line, the cashier begins to serve that customer. After an appropriate service period, which you must also model in some way, the cashier completes the transaction with the current customer and is free to serve the next customer in the queue. Discrete time. Another assumption often required in a model is some limitation on the level of accuracy. Consider, for example, the time that a customer spends being served by the cashier. One customer might spend 2 minutes, another might spend 6. It is important, however, to consider whether measuring times in minutes allows the simulation to be sufficiently precise. If you had a sufficiently accurate stopwatch, you might discover that a customer actually spent 3.14159 minutes. The question you need to resolve is how accurate you need to be. For most models, and particularly for those intended for simulation, it is useful for introducing the simplifying assumption that all events within the model happen in discrete integral time units. Using discrete time assumes that you can find a time unit that, for the purpose of the model, you can treat as indivisible. In general, the time units used in a simulation must be small enough that the probability of more than one event occurring during a single time unit is negligible. In the checkout line simulation, for example, minutes may not be accurate enough. Two customers could easily arrive in the same minute. On the other hand, you could probably get away with using seconds as the time unit and discount the possibilities that the two customers arrive in precisely the same second. Although the checkout line example assumes that the simulation time is measured in seconds, in general, There's no reason you have to measure time in conventional units. When you write a simulation, you can define the unit of time in any way that fits the structure of the model. For example, you could define a time unit to be 5 seconds and then run the simulation as a series of 5 seconds interval. Events and simulated time. The real advantage of using discrete time units is not that it makes it possible to work with variables of type int instead of being forced to use type double. The most important property of discrete time is that it allows you to structure the simulation as in the loop in which each time unit represents a single cycle. When you approach the problem in this way, a simulation program has the following form. Within the body of the loop, the program performs the operation necessary to advance through one unit of the simulated time. Think for a moment about what events might occur during each time unit of the checkout line simulation. One possibility is that a new customer might arrive. Another is that the cashier might finish with the current customer and go on the serve the next person in the line. These events bring up some interesting issues. To complete the model, you need to say something about how often the customers arrive and how much time they spend at the cash register. You could and possibly should gather approximate data by watching a real checkout line in a store. Even if you collect that information, however, you will need to simplify it to a form that captures enough of the real world behavior to be useful. Is easy to understand in the terms of the model. For example, your surveys might show that the customers arrive at the line on an average once every 20 seconds. This average arrival rate is certainly useful input to the model. On the other hand, you would not have such you would not have much confidence in a simulation in which customers arrived exactly once every 20 seconds. Such an implementation would violate the real world condition that customers' arrival have some random variability and they sometimes bunch together. For this reason, the arrival process is usually modeled by specifying the probability that an arrival takes place in any discrete time unit instead of the average time between arrivals. For example, if your studies indicated that the customer arrived once every 20 seconds, the average probability of a customer arriving in any particular second would be 1.20. If you assume that arrival occur randomly with the equal probability in each unit of time, the arrival process forms a pattern called Poisson distribution. You might also choose to make simplifying assumptions about how long it takes to serve a particular customer. For example, the program is easier to write if you assume that the service time required for each customer is uniformly distributed within a certain range. If you do, you can use the random integer function from the random.h interface to pick the service time. Implementing the simulation. Even though it is longer than the other programs in this chapter, the code for the simulation program is reasonably easy to write and appear. The core of the simulation is the loop that runs for the number of seconds indicated by the parameter simulation time. In each second, the simulation performs the following operations. Determine whether a new customer has arrived, and if so, add that person to the queue. If the cashier is busy, note that the cashier has spent another second with the current customer. Eventually, the required service time will be complete, which will free the cashier. If the cashier is free, serve the next customer in the waiting line. The waiting line itself is represented naturally enough as a queue. The value stored in the queue is the time at which that customer arrived in the queue, which makes it possible to determine how many seconds that customer spent in the line before reaching the head of the queue. The simulation is controlled by the following parameters. Simulation time, this parameter specifies the duration of the simulation. Arrival probability, the parameter indicates the probability that a new customer will arrive at the checkout line during a single unit of time. In keeping with standard statistical convention, the probability is expressed as a real number between 0 to 1. Minimum service time, maximum service time. Those parameters define the legal range of the customer service time. For any particular customer, The amount of time spent at the cashier is determined by picking a random integer in this range. When the simulation is complete, the program reports in the simulation parameters along with the following results: the number of customers served, the average amount of time customers spend in the waiting line, the average length of the waiting line, so now we can look at the code. This program simulates a checkout line such as one you might encounter in the grocery store. Customers arrive at the checkout stand and get in the line. Those customers wait in the line until the cashier is free, at which point they are served and occupy the cashier for a randomly chosen period of time. After the service time is complete, the cashier is free to serve the next customer to the line. The waiting line is represented by a queue int, in which the integer value stored in the queue is the time unit in which that customer arrived. Storing this time makes it possible to determine the average waiting time for each customer. In each unit of time up to the parameter simulation time, the following operations are performed. Determine whether a new customer is arrived. New customers arrive randomly with the probability determined by the parameter arrival probability. If the cashier is busy, note that the cashier has spent another minute with that customer. Eventually, the customer's time request is satisfied, which frees the cashier. If the cashier is free, serve the next customer in the line. The service time is taken to be a random period between minimum service time and the maximum service time. At the end of the simulation, the program displays the parameter and the following computed results: the number of customers served, the average time spent in the line, the average number of customers in the line. So we made the simulation time as 2000, average probability is 0.10, minimum service time is 5, and the maximum time is 15. So first of all, we are doing randomize, then run simulation. Run simulation function is making a queue and making the service time remaining as 0, n served as 0, total wait as 0, and total length as 0. We are doing the simulation in a for loop until the simulation time. If random chance arrival probability q.nqt, if service time remaining is greater than 0, service time remaining minus minus. If the service time remaining is 0, n served plus plus. Else if the queue is empty, total wait t minus, or if the queue is not empty, total wait plus equals t minus q dot dq. Service time remaining, the random integer. Total length plus equals queue size. Report results. What is report results? It's just printing some, it's just some print statements. For example, the following sample runs run shows the result of the simulation for indicated parameter values. As you can see, doubling the probability of arrival causes the average time to grow from approximately 5 seconds to over a minute and a half, which is obviously a dramatic increase. The reason for the poor performance is that the arrival rate in the second run of the simulation means that the new customers arrive at the same rate at which they are served. When this arrival level is reached, the length of the queue and the average waiting time begin to grow very quickly. Simulations of this sort make it possible to experiment with different parameter values. Those experiments in turn make it possible to identify potential sources of trouble in the corresponding real world systems. Okay, I'm a bit tired. Let's continue after a break.